Algebra 1, Section 5.7, describing number patterns, or more specifically, arithmetic sequences. And we start with a few definitions. This is something I copied off a Word document in years, something I've used in years past. I guess I copied the cursor right in there too. Inductive reasoning is just making conclusions based on patterns you observe. That really doesn't mean anything to you, except that that's what we're going to be doing in this section. I don't need you to know the word inductive reasoning. You've probably heard the word conjecture before, to just kind of make a conclusion about what the next thing is going to be. And here it says a conclusion you reach by using inductive reasoning. A sequence is a pattern of numbers, so a list of numbers that we can identify what's going on, and again, maybe make predictions, make a conjecture about what would come next once the sequence has ended or has become unknown at a certain point, the next number that is. And then all that to just say this: an arithmetic sequence is a sequence you form by adding a fixed number to each previous term. The fixed number is called the common difference. Now, one way to do this, actually, let me show you this something real quick on the calculator. One way to do this on the calculator is to do what's known as recursive calculation of an arithmetic sequence. And I'm pulling up my graphing calculator here to show you this, but in fact, you can do this just the same on your scientific calculator. Let's suppose that the first term is 4 and that the common difference is 3. You're going up by 3. So the first term is 4, the second number is 3, and the common difference is 3. The second number then would be 7. You have 4, you add 3, you get 7. So your sequence is starting to develop, and it's 4, 7. Go ahead and go plus 3 again and push enter. That was just 3 keystrokes. Plus 3, enter. And it gives you 10. That would be your third number. Now from here, all you have to do is push enter, and your calculator will give you the next number, the next number, the next number. Your calculator has recognized what the pattern here is, and it just starts to add it for you. You don't have to go plus 3, enter, plus 3, enter. You just have to go enter, 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 and it starts to give you those numbers. This is what's known as calculating recursively. Think of recursive, you think if it's recurring, like it's happening again and again, you're adding 3, you're adding 3, you're adding 3. Okay, so that's recursive. And there are formulas for recursive. We've decided to leave that out of the curriculum this year, but there is one. Now, again, use the one that I just used, the example that I just gave, and it was 4, 7, 10, 13, 16, etc. I'm adding 3 each time. ... just means that it continues. Okay. Now, in function notation, like they're giving us here, and by the way, Algebra 2 changes this, and rather than doing a of n, they do a sub n. Okay, I'll show you what that means in a second. But basically, the way our book does this is a of 1. They're using that function notation. This is a of 2. 10 is a of 3. This is a of 4. Why is that? Well, because when I do a of 1, and the first term, now let me make some definitions here. The a value here, the lowercase a value, that's the first term. The d, that's the common difference. This common difference, that's what that is. Okay, so that's the number that it's going up by, or down by too, if it happens to be going down. So a of 1 is equal to the first term, which was this 4, plus n minus 1. Excuse me, the n is itself this number though, right? You see a of n, and then we made this 1. So really that should be 1 minus 1 times the common difference 3. Okay? And what does that give? Well, 1 minus 1 is 0, times 3 is 0, plus 4 would be 4. So a of 1, this is equal to 4. Do a of 2. That would be the first term 4. 4 is still the first term. It doesn't mean the previous term, it means the first term. So it's always 4 plus n minus 1, the n is 2 this time, times 3. 2 minus 1, I'm doing orders of operation correctly here. When I go 2 minus 1 is 1, times 3 is 3, plus 4 would be 7. A of 2 is 7. Do a of 3, you'll get 10. Do a of 4, you'll get 13. Let's just prove it on here. This would be a of 6. A of 6 is 4 plus 6 minus 1, n minus 1, and you replaced the n with 6, so you replace n with 6 here, times the common difference 3. The parentheses would evaluate to 5, times 3 is 15, plus 4 would be 19. I think of these like their names, right? What I'm about to highlight. A of 1, A of 2, A of 3, A of 4, A of 6. These are names, okay? Out here further, you'd have maybe capital A of n that we don't know the n value, right? The one prior to it, this is going to blow your mind a little bit, but the one prior to it would be A of n minus 1. That's one less than it, right? Just like A of 4, and then this is one less than A of 3, and this is one less than that A of 2. The one after this would be A of n plus 1, okay? And then just one more thing, and this is only has consequence in the next class you take, Algebra 2, A sub 1, A sub 2, A sub 3. They change the naming system a little bit. This would be 4, A sub 5, A sub 6. Okay, but that doesn't matter now. We're going to use the function notation like they did here. Okay, so that's what an arithmetic sequence looks like as we go to calculate it. Here's how it is actually in practice. Use inductive reasoning to describe the pattern, then find the next two numbers in each pattern. Here you have 1, 5, 9. You see it's going up by 4s, right? To get from 1 to 5, you add 4. To get from 5 to 9, you add 4. That's what they're showing there. So wouldn't you think to find the next number, you'd add 4, so 13, and then again you'd add 4, so 17. This is using inductive reasoning. By the way, 1, 5, 9, 13, 17, they're going up by the same number. This is an arithmetic sequence. What about 1, 3, 9? Think about how we could do that. See, from 1 to 3 is you're only adding 2. 3 to 9, you're adding 6. This is not an arithmetic sequence, but we could still use inductive reasoning to figure out what the next two numbers are. Did you think of it? Pause the video if you don't want to know the answer yet. They're multiplying by 3. This is times 3. This is times 3. So the next number, if I multiply by 3, would be 27. If I do that again, times 3 would be 81. Okay? Now the ever fun part C here, 1, 9, 25, 49. Pause it again if you want to think about it for a moment. This is 1 squared, 3 squared, 5 squared, 7 squared. It looks like it's the odd number squared. The next one would be 9 squared, 81. The next one would be 11 squared, 121. This is using inductive reasoning. Only the first one was an arithmetic sequence. Find the common difference of each arithmetic sequence. How do you get from 5 to 2? They just gave it to us, by the way, that it is an arithmetic sequence, so there will be a common difference. How do you get from 5 to 2? You would subtract 3. How do you get from 2 to negative 1? Subtract 3, subtract 3. Now listen, when we ask for the common difference, this is very important. Don't say subtract 3. Don't put the operation in with the number. The common difference is negative 3. Okay? Now, I hope that sounded different to you. I'm not saying subtract 3. I'm saying add negative 3. The common difference is negative 3. Basically, the common difference goes like this. Let's use the second example here. Take the current term, subtract the previous term. That's the common difference. 17 minus 14 is 3. Take the current term here, subtract the previous term. 14 minus 11 is 3. 11 minus 8 is 3. The common difference here would be 3. But if you did this here, negative 4 minus negative 1, that's negative 3. The common difference in this case, since it's going down, is negative 3. Again, it's not take away 3 or subtract 3. The common difference is the number negative 3. All right, lastly, find the first, fifth, and 10th terms of the sequence that has the rule a of n is equal to 15 plus n minus 1 times 5. All right, so let's do it this way. A of 1 is equal to 15 plus 1 minus 1 times 5. A of 5, the fifth term, right, is equal to 15 plus 5 minus 1 times 5. The 10th term, that would be A of 10, equals 15 plus 10 minus 1 times 5. And then we'll just do the simple math on that. Now, did you get this from the start, that this number is the first term? So we already know that this is a of 1. This is going to prove it here because 1 minus 1 is 0, times 5 is 0, plus 15 is 15. It was already evident in the equation, but it is in fact 15 when you do the calculation also, of course. 5 minus 1 is 4. 4 times 5 is 20, plus 15 would be 35. 10 minus 1 is 9, times 5 is 45, plus 15 would be 60. Okay, and these are your three answers. Now I just want to make sure you understand as we kind of wrap up this lesson. The first term is 15. The second term, third term, fourth term, I don't know. The fifth term is 35. The sixth term, don't know. Seventh term, don't know. Eighth term, don't know. Ninth term, don't know. The 20th term would be 60. Would it be easy enough to fill in the gaps? Can you tell? Isn't it going up by fives? See how consistent that is? They only told me to find the first, fifth, and 10th terms. So I did it by plugging in and calculating. But really, I could have just found the sequence there. Here's a of 1. Here's a of 2, a of 3, a of 4, a of 5, which they asked me for, a of 6, a of 7, a of 8, a of 9, a of 10, which they asked me for. Okay? I'm saying a of 10, function notation. All right, thanks for watching.